Hello friends, today we are going to see the new chapter Hardness of Metals. Hardness is one of the most fundamental mechanical properties of metals, directly influencing their usability in engineering, manufacturing, and structural applications. It represents a material's ability to resist localized plastic deformation, usually by indentation, scratching, and wear, while strength, ductility, and toughness are also vital mechanical parameters. Hardness is often used as a quick indicator of material duct quality because it is relatively easy to measure and correlates well with other properties such as tensile strength and wear resistance. The concept of hardness has been studied for centuries, beginning with early comparative scratch tests such as the Mohs scale and evolving into highly precise modern techniques like Rockwell, Vickers, and instrumented nano indentation. In industrial contexts, hardness testing plays a critical role in quality control, material selection, heat treatment, verification, and failure analysis. Then we are going to see the definition of hardness. Hardness can be broadly classified as the resistance of material to permanent deformation. In metals, this deformation usually occurs through plastic flow or dislocation movement under localized loading. Depending on the context, hardness may be described in three different ways. Scratch hardness means resistance to scratching or abrasion. Example is Mohs scale. Indentation hardness resistance to localized plastic deformation caused by an indenter. Example Brinell, Rockwell, or Vickers hardness tester. Rebound hardness resistance to elastic deformation measured by the height of rebound of an impacted body, like Shore scalerometer. Among these, indentation hardness is the most commonly used in engineering because it is quantitative reproducibly and directly correlated to tensile strength and wear resistance. Hardness in metals is strongly linked to the underlying atomic and microstructure mechanism that govern plastic deformation. The key principles includes dislocation motion. Metals deform plastically by the movement of dislocations. Hardness increases when dislocation motion is restricted by obstacles such as grain boundaries, solute atoms, or precipitates. Strain hardening. Repeated deformation introduces more dislocations, which interact with each other and make further movement difficult, thereby increasing hardness. Grain size effect, Hall-Batch relationship. Smaller grain size provide more barriers to dislocation motion, increasing hardness. Solid solution and precipitation hardness. Alloying element can distort the crystal lattice or form precipitates, both of which impede dislocations and improve hardness. Work hardening. Cold working process like rolling or drawing increases dislocation density, which enhances hardness. Thus, hardness is not merely a superficial property, but a manifestation of a material's microstructural resistance to plastic flow. Methods of measuring hardness. The first is scratch hardness. Mohs scale, one of the oldest methods, developed in 1812 by Friedrich Mohs. It is a relative scale ranking minerals from 1 to 10, that is talc to diamond, based on their ability to scratch one another. Metals typically range between 2 lead tin and 8 tungsten carbides. Limitations: qualitative, not precise for engineering design. Indentation hardness. This is the most widely used category with several standard methods. First is Brinell hardness test, that is BHN. Uses a hardened steel or tungsten carbide ball indenter. Load is applied and the diameter of indentation is measured. Brinell hardness number is equal to load divided by surface area of indentation in mm square, and that is suitable for large coarse grained metals like casting and forging. Then Rockwell hardness test HR scale मध्ये uses a conical diamond or a steel ball indentator, measures depth of penetration under minor load and major loads, provides direct reading on Rockwell scale ABC, widely used in industry due to simplicity and speed. Example Rockwell C scale HRC is common for hardened steels. Weaker hardness test VHN or HV uses a square based diamond pyramid indenter. Load apply, then diagonal lengths of indentation measure. Formula allows calculation of hardness independent of load, making it a universal method. suitable for both very soft and extremely hard metals. Then is Snoop hardness test. Uses an elongated diamond pyramid, ideal for thin materials, coating, microstructures, and common in metallography. Then rebound hardness, Shore scleroscope. Measure rebound height of a hammer dropped from a fixed height. Lib hardness test, portable device measuring rebound velocity ratio, useful in situ hardness testing of a large components. Nano indentation, modern methods using a sharp indenter with nanoscale loads and displacement. Provide depth independent hardness, elasticity, modulus, and creep properties, essential for coating thin films and advanced alloys. Factor affecting hardness of metals. First is chemical composition. Alloying elements like carbon, chromium, vanadium, and molybdenum increases hardness. Example, steel hardness increases with carbon content. The second factor is heat treatment. Quenching, tempering, annealing, and case hardening strongly modifies hardness. Quenching produces hard martensite. Tempering adjusts hardness, toughness balance. Then microstructure. Fine perlite, martensite, and benite are harder than coarse perlite and ferrite. Precipitation hardened alloys exhibit very high hardness due to nanoscale obstacles. Then fourth factor is cold working. Processes like rolling, drawing, or stamping increases dislocation density, enhancing hardness. Then fifth factor is temperature. Hardness generally decreases at elevated temperatures due to thermal activation of dislocation movement. High temperature alloys are specifically designed to retain hardness under service conditions. The sixth factor is grain size. Smaller grains means more grain boundaries and more hardness, that is high hardness. Hall batch relation shows hardness is inversely proportional to the grain size. Industrial importance of hardness. Quality control. Hardness testing is a quick, non-destructive method to verify metal conditions, used to check consistency of heat-treated parts. Material selection. Hardness correlates with wear resistance, making it crucial in selecting metals for cutting tools, bearing, gears, and dies. Strength estimation. Tensile strength of steel can be estimated from hardness. Failure analysis. Hardness mapping across a failed component reveals variation in heat treatment or service degradation. Surface engineering. Processes like carburizing, nitriding, and hardening are evaluated through surface hardness measurement. Coating and thin films. Micro hardness and nano indentation techniques assess protective coating for corrosion and wear resistance. Hardness of common alloys and metals. Aluminum and alloys. Low hardness 20 to 100 HV. Improve with heat treatment 2000 to 7000 series alloys. Copper and alloy brass. Bronze. Moderate hardness increases with cold work. Steels. Wide range. Annealed steels 120 to 180 BHN. Quick quench and temper steels more than 600 HV. Titanium alloys, high hardness to weight ratio, excellent for aerospace material. Tungsten carbide, extremely high hardness, 1500 to 2000 HV, used in cutting tools. Challenges and limitations of hardness testing. Non-uniform microstructure. Hardness may vary across a part, making localized testing less representative. Surface preparation. Indentation methods require smooth, clean surfaces. Size effects, thin coatings, or microstructure require specialized micro-nano hardness test techniques. Conversion issues, hardness values from different scales are not always directly comparable. Temperature sensitivity, hardness tests at a room temperature may not reflect service condition. Recent developments, instrumented indentation records continuous load displacement data, allowing more precise hardness and elastic modulus evaluation. Automated hardness mapping, computer control testers create hardness profiles across a sample. High temperature hardness testing, specialized equipment, hardness at service-like conditions. Correlation with computational models, molecular dynamics, and finite element simulation are being used to predict hardness from atomic structure. Then what we got, that is conclusion. Hardness is a vital property of metals, reflecting their resistance to plastic deformation, wear and scratching. Although it appears simple, hardness embodies complex microstructural phenomena such as dislocation movement, grain size effects, and phase transformations. Its measurements is central to engineering practice, with methods ranging from the basic Mohs scale to advanced nano indentation techniques. The importance of hardness extends beyond laboratory testing. It directly influences design, manufacturing, heat treatment, and performance evaluation of metallic components. Whether in quality control of steel gears, durability testing of aerospace alloys, or characterization of protective coatings, hardness remains the cornerstone parameter in material science and metallurgy. As technology advances, hardness testing is becoming increasingly precise, automated, and capable of nanoscale measurement, ensuring its continued relevance in modern materials engineering. Then you see the references. Thanks for the watching video.